In this video, I'm going to cover Chapter 7 in the data link layer. So far in this class, we've worked our way down the OSI model, and in this chapter, we arrive at the data link layer. In this chapter, I will describe some of the key components of the data link layer and a little on how it works. The data link's main responsibility is to prepare communication for transmission on a specific media. If you take a look at this computer lower left, it's going to send over copper media, and then the router will accept the data, and then the router is going to send it over fiber optic media with light pulses. The satellite will receive it and send it wireless over to the other satellite dish, which will then in turn send it over fiber optic and light pulses to a wireless router, and the wireless router will send it as radio waves to the other computer. So along this whole entire path, we are going through different types of media. The data link layer is required to prepare the data to be sent over each one of those media types and is required to control access to that media. What's inside of the message never changes. What we do at each hop is we decapsulate and encapsulate that IP packet and form it in a way in which we can send over each type of media. The data link layer is broken up into two different sections, a software and a hardware layer. Some of the pieces of hardware that work at the data link layer are a network card and switches. These are known as layer 2 devices. But these devices also have some software components of them. For example, a network card has a driver. That driver is a piece of software that lets the network card interact with the operating system. So because of this, we have some portions of the data link layer that are implemented in software and some portions of the data link layer that are implemented in hardware. There are many different protocols and standards used by the data link layer, and some of the most common ones are from the IEEE. For example, the 802.3 standard is a standard defined for Ethernet. This is going to define how we package our data to be sent over copper Ethernet. 802.11 is wireless LAN. 802.11 is going to dictate how we package our data to be sent over wireless transmission. Again, remember, the data link layer is responsible for packaging our data to be sent over different types of media. At the data link layer, we control access to the media. Without any control, we could potentially get what are called collisions. Collisions happen when two or more hosts send at the same exact time, and their data they try to send collides on the media. There are some different methods that we have in order to maintain access to the media, and some of these are taking turns and others are listening for absence of signal. The data link layer is responsible for controlling access to the media. There are two main ways that the reading talks about and how we control access. One is controlled access, where only one station can transmit at a time. This is what we see on the left-hand side here. Usually with this, we have what's called a token ring type of environment, where you must have the token to be able to speak on the network. This is sort of like what you used to see in classroom settings. If you wanted to talk, you would raise your hand, the teacher would point at you, and then you could go ahead and talk. No one else was allowed to talk in the classroom unless they were to raise their hand and ask for permission to talk. Same things happens with computers in a token ring network. You must possess the token to be able to communicate on the network. And if you want to be able to communicate on the network, and if you don't have the token, you request that token. Once you're given the token, you can now communicate on the network. This is great because we're not going to have any collisions, but it can be a slower process because only one can communicate at a time, and we must wait our turn in order to get that token. The other type of access is contention-based access. And there's two types of contention-based access. One is CSMACD, which stands for Carrier Sense Multiple Access Collision Detection. With this type of access, we can all communicate at the same time. But what we do is we listen for absence of signal on the network, and if we detect that there's absence of signal on the network, we go ahead and we try to send our data. If it happens that two PCs or two devices communicate at the same time and a collision happens, we simply detect that collision, notify the other hosts of that collision on the network, and we resend our data. So again, that's called carrier sense multiple access collision detection. This is used by our wired Ethernet networks. Wireless networks, on the other hand, use carrier sense multiple access collision avoidance. With wireless networks, we can all communicate at the same time. We try to avoid collisions at all costs. With our wireless networks, we have a lot of overhead built in to our packets. Overhead to try to avoid these collisions. When you see a wireless G router rated at 54 megabits per second, the actual throughput and goodput that we are getting is not going to be nearly that high because we have overhead that's built into those packets to try to avoid these collisions at all costs. So again, that's carrier sense multiple access, meaning that we can all communicate at the same time. We try to avoid collisions with wireless networks or 802.11 networks. Full duplex and half duplex is an important concept to get out of this chapter. Full duplex means we can send and receive at the same time. If I want to be able to do full duplex, my PC must be plugged into a switch. Switches allow us to send and receive at the same time, and the concept of collisions happening with a switch goes away. Full duplex can be thought of like communicating on a telephone. When you're talking to somebody on the telephone, you can talk and listen at the same time. You could potentially interrupt them or talk at the same time. Half duplex, on the other hand, is what hubs only support. With half duplex, we either can send or we can receive at one time. That's it. Half duplex is kind of like talking on a walkie-talkie. If you've ever talked on a walkie-talkie before, you either can talk or you can listen. You cannot do both at the same time. If you want to talk, you push in the button and say your message, and then when you want to listen, you release the button, and you can now listen to the person's response. Because of the ability to do full duplex and that collisions will not happen with a switch, switches should be used whenever possible instead of hubs. We need to be able to make the distinction between a logical topology and a physical topology. A logical topology is how transmission occurs between hosts, whereas a physical topology is actually how it's physically laid out, how it's laid out in the room, or how it's laid out in the building. With a logical point-to-point network, we think that we're only communicating directly with one other node or one other device. In this scenario down here along the bottom, the lower left router and the lower right router communicate with each other as if they are the only two devices in between. When in fact there could be other networks that we're passing through, other topologies that we're passing through. But the point is, logically, we think we're communicating only with each other, but physically there could be other devices in between. In a multi-access topology, we all have access to the same media. Usually what we see with a multi-access topology is a centralized switch here in the middle. All of these devices would be plugged in to the switch. That's typically what you see in any type of modern lab environment, any type of modern work environment, is all PCs that are wired up would go back into a central switch. Now logically we all have access to that same central switch, but physically those PCs could be spread out anywhere throughout the topology. In a multi-access type of network, we're going to use that carrier sense multiple access collision detection, and we will try to detect any collisions that happen and resend our data. But again, if we're plugged into a switch, no collisions are going to happen and we can do that full duplex. This example here is showing a logical ring topology. Now the computers don't have to be physically set out in a ring, but logically what's going to happen when we communicate is the information is going to go from one PC around a ring to all the other PCs. So every single device on the network gets that information. Only the device that's intended for processes the information. So this example here, PC A says I need to transmit to D. So he sends it around the ring. B gets it and B asks itself, is the frame for me? No, he does not process it. C gets it. C says, is the frame for me? No, it's not. He does not process it. Sends it on to D. D gets it. Is this frame for me? Yes. I can go ahead and I can process it and I can send it up the other layers of the OSI model. We said that the data link is responsible for preparing data or encapsulating data to be sent on different types of media. This is very important because over different types of media we can potentially have fragile environments or a more protected environment. In the case of wireless or radio transmission, we have greater effort needed to ensure the delivery because we have other things that can influence that network transmission, like going through walls or other radio wave interference, electrical interference. Because of this, we have higher overhead and slower transmission rates. That's why we have not seen the same speeds with wireless networks as we currently do with wired networks. Because we have that greater overhead, we have a more fragile environment to send our data over. Whereas in a protected environment, like a wired environment, less effort is needed to ensure the delivery. We have a lot lower overhead, meaning we don't have quite as much extra information in our packets, and we have faster transmission rates because of this. That's why we see a lot faster speeds with our wired networks compared to wireless networks. At the data link, we are working with what are called frames. We take our packet from the network layer and we encapsulate it into a frame. Inside of the header of a frame, we have some important information, and probably the most important information is our addresses. We have our MAC addresses added to our frame here at the data link layer. The MAC address is an address that's burned into a network card. That MAC address is a 12-digit hexadecimal number that is unique to every single network card in the world. We communicate with MAC addresses in our local area network, in between our local topologies. When we want to communicate outside of our local area network, then we use our IP addresses. At the end of the frame, we have an important piece called the FCS, or the frame check sequence. This is a number that's calculated before the frame is sent out. And when the receiving device gets this frame, it recalculates the FCS. And if they match, we know that that data has not been altered or changed in any way. If it does not, we know that that frame is potentially corrupt or bad, and we will resend for the information. That is all for this video on the data link layer. Again, the data link layer is responsible for preparing data transmission over different types of network media. It's also responsible for controlling access to that media, such as using carrier sense multiple access collision detection, or using like a token ring type of environment, where you have to have the token to be able to communicate. I encourage you guys to read the chapter to go along with this video. And if you have any questions, please let me know. Thanks for watching.